In today's lab, we are going to investigate and explain the relationships between electricity, current, voltage, and resistance. Before we get started, let's go over these terms. You're probably familiar with electricity as you use it every day. However, technically, electricity is created by the movement of electrons. Voltage is the difference in charge between 2 points, while current is the rate at which the electrons or charge is flowing. Lastly, resistance refers to a material's likelihood to resist the charge or current. It is also important that you understand a couple of different laws. Ohm's law states that the voltage across a conductor is proportional to the current that runs through it. Kirchhoff's law states that the voltage changes in a closed circuit are equal to 0. Today I'm going to be building a variety of different circuits, and there are actually 2 different types. In a series circuit, the amount of current is the same through each component of the circuit, and total resistance equals the sum of individual resistance. In a parallel circuit, there are 2 or more paths for the current to follow, the voltage is the same across each component, and the current in each path is equal to the current that flows from the source. Like I said, I'm going to be building a variety of different circuits today and explaining their importance as I go along. You will have some questions to answer as I build the circuits, and once I'm finished building the pre-designed circuits, you will also be designing a circuit yourself using the parts that you saw in the video. If you haven't finished the introductory questions yet, you might want to pause the video. If not, let's build some circuits. The first circuit I'm going to build is simply a basic light circuit. Now that it's been assembled, I'm going to use the switch to turn the light on and off. When the switch is closed, electric current flows from the positive pole of the batteries through the bulb to the switch and back to the negative pole of the batteries, turning the light on. This creates a closed circuit. Opening the switch disconnects the flow of electricity and causes the lights to go off. This creates an open circuit. Now I'm going to replace the switch with a component called a reed relay. This setup will give a magnet the ability to control the flow of electricity. When the 2 metal reeds become magnetized, they connect, closing the circuit and turning the light on. Now I'm going to mount the fan blade to the motor and turn the switch on. This setup translates electricity to mechanical rotary motion, which is made visible by the spinning fan. Now once again, I'm going to replace the switch with a magnet. This setup allows the fan to be controlled by the magnet. Now that this circuit is assembled, I'm going to place the fan on the motor and turn the switch to the on position. This current has a series configuration, which means the electric current in each connected component is the same. Now I'm going to place the fan on the motor and turn the switch on. This circuit has a parallel configuration, which means the voltage of each parallel connected component is the same. In this setup, the two battery groups are in a parallel configuration. When the same voltage of battery groups is used in parallel connection, the total voltage stays the same as one battery group. Here, it's 3 volts. Now that I've assembled the circuit, I'm going to mount the fan to the motor and press and hold the button. When the fan spins, the force of air is pointing upwards, just as it does when you use an everyday fan. I've now exchanged the positive and negative side of the motor by flipping the fan around, and once again I'm going to mount the fan and then push and hold the button. The turning direction of the fan will change, and the air is now being pushed downwards. This is the principle of a helicopter, but in this case it won't produce enough force to lift the circuit into flight. The reed relay circuit, which I have assembled here, is a switch device controlled by a magnetic field. When you flip the switch, only the LED turns on because there is not enough power for the bulb. When moving the magnet close to the reed relay, the two reeds inside connect and close the circuit. The LED will then turn off and the bulb turns on. This is because the electric current takes a shortcut through the low resistance reed relay circuit. Now I'm going to replace the bulb with the motor. Using the magnet to control the reed relay, the LED and the fan can run alternately. In this circuit, once it is turned on, the magnet and reed relay can be used to control the intensity of the light. The alarm box I'm using in this circuit stores the sounds of a police car, jackhammer, fire truck, ambulance, and game machine. We can get various sounds by using different circuit assembly. The assembly of this circuit should play the police car siren when I turn on the switch. I will now remove the 3-snap wire pad between C and D and connect A and B. This should produce the sound of a jackhammer. Now I'm going to remove the 3-snap wire pad between A and B and connect E, F, and CD. This will produce the sound of a fire truck. Now I'm going to remove the 3-snap wire pad between EF and connect CD and AB. You should now hear the sound of an ambulance. Now I'm going to remove the 3-snap wire pads between AB and CD and connect E and F only. You can now hear a game machine. I'm now going to replace the speaker with both the LED and traditional light bulb. The goal here is to make the bulb flash. Record the results for both the LED and traditional bulb and explain the differences or similarities you saw. This brings our lab to a conclusion. Make sure you've answered all the questions on your handout and recorded all the information you need.